Today, we are running another agentic AI use case, focusing on text-to-SQL, especially for enterprise data analytics, which has its own domain-specific complexities. And this talk is based on the paper from LinkedIn. This paper is presented in the workshop on agentic AI for enterprise at the KDD this year in August. So it's a pretty new paper. And actually, I'm glad that they published this so that we can glimpse into like more details of how they can set up the AI agents for a specific enterprise application. Before diving in, let's, as always, look at what is the use case, right? I think, as the title says, it's pretty straightforward, text-to-SQL. It can be an easy one, right? Like, for example, what is the number of cars with more than 4 cylinders? And then it's basically say the car's data has all the information, like one table has all the information, and you can just do a count and with the where clause. There can be also a hard SQL. The hardest one even can even longer SQL than this one. But this shows the example of the complexity of SQL, where like one single table does not contain all the information you need, right? Like which countries in Europe have at least 3 car manufacturers. You need to join lots of tables, like from the countries, from the car makers, etc. over here, right? So it's and also you need to do the group by and then doing some counting and the condition. So this also shows like the integration of different tables and able to perform the right logics in order to answer the request of the question. Before actually, when we are trying to deploy any AI agent solution in enterprise, the first part is we should ask the right question. So people, I think you all see the joke right now flying around on the internet. It's like, oh, what we should do now is like, oh, we should all do Gen AI. But a Gen AI without the right requirements or not clearly defined scope is going to fail, right? So whenever you are building a Gen AI applications, you should think about, okay, what is the problem to begin with, and what are exactly the requirements that the AI agents needs to meet. For example, in this case, the text-to-SQL, I think the first key requirement is this agent should be able to understand the domain-specific semantics, right? Like your enterprise may have all lots of tables, right, with the different schemas and also the columns. And also you may have your own domain knowledge, right? So this agent should be able to understand all this semantics and then able to retrieve the right information or right context for the user question. And then it should be able to generalize to a large and evolving data lake, which can be at minion scale. So in this paper, because it's LinkedIn, so I think they are managing lots of tables. It's like millions of tables they need to manage. So they set up this AI agent to be able to work for millions of tables, but can get back the say the final SQL say around 1 minute. And then the third requirement could be like you should also define this end user utility, right? How the users is able to interact with this AI solution. So this paper also shows that how they can design this chatbot. And also like in the same view with the SQL editor. So for the users to easily paste the auto-generated SQL into the user SQL editor and to modify as needed by themselves. Before looking into the agentic AI, actually the first questions I have is, what is the performance of single LLM, right? I think also in the past meetup, my recommendation is always to start with one LLM first to see what is the performance, whether we really need multi-agent framework. So you will be very interesting to look at, okay, what is the performance if I just pass the question to the LLM and just trying to solve the question with one LLM code. And in literature, there are like this different different benchmarks over here, like from the Spider 1.0, which is the relatively simpler benchmarks. And top models can achieve like above 90% accuracy. And then people say, oh, I need a more complicated benchmarks that can represent the full complexity of enterprise analytics tasks. And then the BERT, also Spider 2.0 benchmarks was proposed, and then the GPT 4.0 kind of dropped from nearly 90% to only 13% on a more complicated enterprise scenario. And even the more recent release of 0.1 or 0.3 is also fluctuating around between 20 to 30%. So it means that there's a big gap for a single LLM to be able to perform very well on this text-to-SQL test. Also, there's some internal evaluations, say, by Snowflake. They also test the GPT 4.0, and then it shows the accuracy of 51%. So all of these benchmarks emphasize the challenges of the real-world business. If you are interested, you can just search Spider 2.0 leaderboard, and then the first link should gives you this leaderboard. So if you look at the current ranking, right? So the rank 1 is actually published just 3 days ago. It's from the Alibaba Cloud Computing Platform, and it's able to score of 61% accuracy on the complicated benchmarks. And again, it's agent, right? So you see all the top ones right now are agent here. And if you look at the single ones, I think this reinforced plus 0.3, well, it's still a little bit a simple agent plus 0.3. It only gives you like a 33% accuracy. Well, with a more complicated, like more specifically designed for the text-to-SQL agent platform, can improve the performance to 60%. So this paper from LinkedIn, the key contribution of this paper is first, they propose, to tackle the challenges of understanding the data semantics. They construct a knowledge graph, right, from the table schemas, from the documentation they have, even the coding repositories of all the SQL examples in the past, and also historical query logs. And also they integrate some to understand the company jargons, right? Like I say, you have lots of abbreviation names and product names and lots of short abbreviation, which will be very difficult for the company, for the LM to understand. So basically they kind of organize all the information about the enterprise into a knowledge graph, which I'm going to show the structure later. And then to write queries, they design the architecture for the query writer agent. It uses a multi-stage retrieval, kind of retrieve all the likely context, ranking the tables, right? So kind of like select the top K instead of sending all the retrieved components to the query writer, so that they try to improve the context provided to the query writer to generate the best query as possible. And then they also develop the interactive chat UI that can help the user to understand the query and able to interact with the bot directly. So this is the knowledge graph they built to organize the enterprise data. So the enterprise data, well, I think it also depending on which industry you are in, right? So I think this is more kind of for LinkedIn, which is kind of like a professional social platform. So basically, like they have a company, right, LinkedIn, and then it contains like a different products, right? And then each product may have its own domain knowledge. The domain knowledge is drafted by the user. And then the user, like each user may have a dedicated products that they are working with. And then, so you also have lots of tables to manage, right? Regardless of the industry, say you are using a database and you have lots of tables to manage. And the table, of course, like contain the columns. And then each user also belong to a user group, which have access to the table. And the user may also write lots of queries in the past or submit the tickets or codes, right, in the past. So these are all the data generated by the user in the enterprise setting. And then in this work, they also propose to build a table clusters to organize the tables. so that the table has similar semantic meanings, kind of can be put together in one cluster, so that the user, when you retrieve, you can retrieve based on clusters instead of retrieve based on one. Say you have like 1 million tables, so they kind of doing some dimension reduction to organize the tables in clusters. So this is the knowledge graph they built, but I do believe this knowledge graph can be expanded to integrate additional data sources you have. Say if you want to build a chatbot to answer any questions about the company, around the supply chain data, product data, kind of the oil supplies data, right? And then you should be able to build this relation graph, kind of like the knowledge graph, organizing all the knowledge or data in your company. And of course, like for each graph node, you may have the attributes, right? Like for the table, you can have the database name, table name. You can have the descriptions, no matter it's drafted by human or drafted by AI. Yeah, you can draft a description about the table by AI. Usage popularity, like how often the user queried about the table, right, etc. And also the column, I think is the same, like the human or AI description and which table, usage popularity, data type, and column type, etc. So these are also kind of more like semantic information to provide more context around the table and the column for the LLM agent. So one important thing the paper proposed is that we should organize the table in clusters, because they have millions of tables and not all of them are relevant to every product or user. So instead of managing millions, they do a dimension reduction so that they can, so maybe instead of millions, maybe we can organize it by hundreds or like 1,000, right? So it's in a manageable size, and also able to improve the latency of the system. So how they do this? They prepare the user dataset access data. So it is like a matrix, right? Like the rows can be a data set and the columns are the users. And then you build this access count for the user dataset access count, right? And then recording which user access which data. So you have this big, huge matrices. And then you may want to do some filtering out some of the noise. If the number is too small, you may want to filter it out and then scale the data so that you have, for each user, you have a mean of 0 and standardization of 1 across the data sets per user. And then we can perform the dimension reduction, ICA, to these matrices. And then we can have a score for each table component. So component right now kind of represents the table cluster, right? And then for each table component, you get a score. And that score, that kind of tells you how similar or how likely that the table should belong into that component, which is the table cluster representation. And then you can create this cluster, right? So basically using this component, which represent the cluster, you can identify the tables has the highest scores associated to that component. And then they also do some extension, like each data set should also be assigned to the top component to make sure that every table is assigned to at least one cluster. So over here, after they doing this, create the data cluster, right? So right now, every table has its own cluster. They also assign users to the clusters, right? So right now, they, instead of like big matrix, where you have the user and table count, access counts, big table. Right now, you aggregate that big table into user and cluster counts. And so basically, you can aggregate it into a much, much smaller table to determine like the user access counts per cluster. And then for each user, they are going to just assign the top clusters based on their access counts. So this can help, like given a user, whoever the user is, when they ask a question, this is more straightforward, right? Like they can just retrieve the top table cluster for that user. But could there be a miss? I think so. But basically, this is a trade-off between the performance and the efficiency. And then let's move on to the full system design. So this is how they organize the data backend. And then they need to build that chatbot. And then at high level, they build, they actually build an intention classifier first, based on the user question, because sometimes the user question is not necessarily a SQL writing task. It could be just a general Q&As. So basically, like you can have a static classifier router. Based on the intention of the question, you can route the question to the corresponding agent, whether it is asking to write a query, whether it is just looking for which table, like what table can, or some table or some columns that the user is trying to look for, right? This is just a data finder agent. Or the user has faced some difficulty fixing queries, and then they can just directly pass in their queries and ask for help to fix the queries, or just a general Q&As. So this is their high level of classifying the intention of the users and able to call the relevant agent at backend. And then we are going to mainly focus on the query writer agent. In the query writer agent, so the user, right? So the user has a question, natural language question. And then so the user has, belong to certain user groups, and also for each user, there's a specific product areas they are focusing from the knowledge graph. And then here, there are major, like 4 big components here. The first one is to retrieve the context. So this is the RAG idea, right? To retrieve the most relevant tables, retrieve the domain information context, or for example, as Shen asked about the role of the user, right? Some features about the users can all provided as to identify as the potential context as an input. And then they specifically build a LLM to rank the context. Say for out of the retrieve the context, you got 100 tables. And over here for the rank, you may end up just select the top 5. So the rank is kind of to more optimize which is the top K that we are going to select for the query writer. And then the top context is passed to the LLM, another LLM, to write the queries. And then after the query is right, you need this loop. Like validation is basically, I think, it's just an engine to execute the SQL, and then it's able to print out the errors if there's any error, right? And then it's going to pass the errors to a researcher, which is another LLM, to trying to figure out, whether the table is wrong, the column is wrong, how can I resolve this table, or maybe the table name is wrong, right? And then the researcher, this is the LLM agent here, is going to fix these errors based on what error is presented, and then it's going to update the context to the query fixer. And the query fixer is going to update the queries and then do the validation again to make sure that it can resolve the error. So after this can be successfully compiled, and then it's going to execute it, and then it's going to provide the final executed results to the users in the end. So this is a high-level framework. So this is the retrieve, rank, write, and fix. So this four major components here. So if you look into the retrieve part, right? So like let's zoom in a little bit into this. So the retrieve part is basically you're trying to identify all the relevant information you can get from the knowledge graph. Well, the advantage of knowledge graph is like very easy to retrieve the relevant, right? So you can just retrieve the table cluster, the products, some domain knowledge about the products and the company jargons, to better understand the user question there. Say if the question contains some abbreviation of the names, and then if you are using the jargon, you can easily understand what that name is about, right? And also here, there's an example fetcher and table fetcher. And then they use the EBR. EBR is the embedding-based retrieval. So this is exactly the same as the RAG of, based on that question, can I retrieve any similar SQL examples from the past? So the example filter is like, I have a history of all the queries the user write or completed in the past. Can I identify some similar SQLs as examples, right? The question and SQL pairs. as the example from the past. So this is kind of the example fetcher or retrieval based on the embeddings. And then also the table cluster or table embeddings, table fetchers here. And of course, like a column fetcher from the table. So this retrieved context is trying to identify all the information, either directly pull from the knowledge graph, or you can retrieve based on these embeddings, which is the same idea in RAC. After you retrieve the context, you want to do further optimization, right? Maybe out of that, I still got, say, 100 tables. And then I want to do narrow down the initial list of candidate tables into an even smaller and more focused set. So this re-ranker LLM, so it's another LLM call. So the context for this could be more information like the table names, descriptions, all the example queries associated with the table, right? Like to understand whether there's any frequently called query tables, etc., and also the domain knowledge records. So this can all provide as a context to the LLM, and then you can ask the LLM to identify, so basically rank the list of tables and provide you the top K tables from your request, right? Based on the user's question, and then pass to the subsequent query, right? And then I think the last part is the fixed part. I think for any coding or SQL writing, that you like usually make it more like make sure that the SQL or codes can actually run is through this multi-agent framework for fixing the errors, right? So you have a researcher, which is kind of trying to figure out what is wrong and whether it can automatically correct, say, the table names based on the errors. And then there's a loop of just fix the queries, run the validators, pass the errors to the researcher, or if there's no errors, then it can be executed and directly respond with the answers to the users. So maybe we can also look at the LLM agent, the researcher here. Itself is a multi-agent. Well, I think it's just 2 agent. So it's a multi-agent, but it's actually 2 agents. So one agent is a researcher LLM, which is able to access tools to manage the database, for example, to search for the tables, in case say some table names or the LLM hallucinates a new table name, which doesn't exist in your database, right? And then this researcher LLM can specifically kind of call the corresponding search table tool and auto corrects the table names, say, caused by the hallucination of the query writer. And then it's also able to fetch more metadata about the table and able to update the context to the query writer. And then after it's updating this, there will be a kind of like a self-critic or self-reflection LLM to see whether it meets the requirement, like whether whether to say to kind of like as a validation step. To say like whether I need to make more changes, like the context is not sufficient to this researcher LLM, so the LLM can perform additional actions based on the feedbacks, or the self-critic or self-reflection LLM think it's already sufficient to accept the answer and then pass the updated context to the query writer again. So I think this framework is commonly used in any coding agent or like this SQL writing agent to do as a self-reflection to determine when should I stop or I should make more modifications. So let's look at what they develop in the end. So this is the agent architecture design behind scene. And then this is their kind of the internal SQL interface, right? And then, yes, as usual, the user has always their own SQL editor. And then they have also a SQL bot, right? So basically you can just select the, over here, they also give the user a choice of which LLM they want to select as the writer LLM. And then they can choose the LLM over here, like say GPT-4o. And then they can just directly ask the questions, like what are the example questions over here. And then you will get a response directly in the SQL bot. you can just chat with. It's kind of like a co-pilot experience, or you can just copy the SQL from the bot to the editor, right? So you can do all the modification if you want. So this is a final like a deployment stage of what is the interface like integrated directly into each user's SQL editor. And then this is what is the bot output looks like, right? So the bot outputs, there are two stages. One is the table output, right? So based on the question, the bot can automatically suggest like what tables to use. So based on this question, like calculate how many times each post reaction was used in September, like on LinkedIn, right? And then the SQL bot is automatically suggesting which tables to use, and also it also tells you it's like commonly queried with what other tables, kind of tell the users like information instead of you like reading your wikis, to trying to figure out, or reading the table semantic yourself and trying to figure out, okay, what table should I use, right? So they do auto table suggestion here. And also they give a choice to the user if they want to select which table to use after this information is presented. And then after this table is determined, then they are going to write the queries, right, back in. And also they are going to provide some explanations for the queries so that in case there is still some errors, right, they want to help the users to understand the query so that they can help correct the errors on their own. I think this is a pretty good experience of how they want also to improve the user experience of providing some controls to the users. Like if the user want to own more, that they also have the flexibility to select the tables they decide to use, and also to modify the query as they want based on the explanations that the bot also provides along. Then let's look at the evaluation. I think usually like when we develop the AI agent, a lot of time is spent actually on the evaluation part. Like how can we evaluate the AI agent is performing well? And then in this paper, they develop an internal benchmark set, right, to measure the performance. And also because queries, like even to answer the same questions, like one question may have multiple valid queries solutions, say using equivalent tables or similar columns, right? So they also allow like a multiple ground truth responses per question. So they connected 133 questions across 10 product areas. Do you think this is big enough? I don't think this is big enough, but I think using this 133 questions is already a good indicator, at least to tell like initially whether we should launch it, like whether we think it's effective enough to be launched, and then we can track the performance post launch to better reflect what is exactly the underlying performance in production. And also the metric, right? Because this what they deliver is interactive chatbot. So they more focus on the metrics that access the user utility and the user experience. For example, did he find the right tables or columns? Is the query correct or close to correct? For example, like just with a very small minor correction, it works. And also did he respond in a timely manner? So this is more from the user experience angle, whether the latency, do they think it's like take too long to run? So this is more telling like how the latency is affecting the user experience, right? Because sometimes if you think 1 minute is long, but actually for users, maybe that 1 minute is not long. So based on the different applications, I think the latency requirement will be also different. But in this, they specifically like ask the users like whether they think the result is timely or it takes too long to get them output. And in terms of evaluation, they use both human evaluation and also LLM as a judge. So basically, you send the criteria to LLM, and then LLM decide comparing the auto-generated SQL to the ground truth SQL to see whether the SQL are written in a high quality. There. And then they provide a score from 1 to 5. The 5 is the highest score, saying that the bot is able to answer the user question perfectly. There's no change at all, and it just works out of box. And 4, it means that it is almost correct, but there are still some minor issues, and even a non-expert can easily fix it. And then the 3 is like there's the major columns are correct, but there's still gap, right? In terms of like it still requires substantial effort. So in this paper, they more in their kind of acceptance rate, they mainly treat the 4 and 5, either fully pass or just with a very easy minor fixes to the queries, and then it can work. So the success rate is based on like at least scored 4, right? 4 or 5. And then in the experiment setup for the benchmarks, so this is the embedding model they use. The E5 for the example, so this SQL example embeddings to retrieve the similar SQLs from the past history. And then they use the text embedding ADA for the table and column semantic descriptions, etc. The embeddings for the tables. And then they use the GPT-4o mini. All right, so why they choose mini? Because they want to improve the latency. So yeah, basically some trade-off there. Choose the mini, they think is sufficient for the researcher. And then for the others, they choose the GPT-4o published in May last year. The LLM as a judge is also done with the GPT-4o. So all the models are accessed through the Azure OpenAI service. Okay, so this is the results. So when they do the results, they split it into different components. So basically, they want to understand what information is most important to write a right query. So this is all the components from the knowledge graph, right? So if you are using all the components, like all the information in the knowledge graph, what is the recall, like whether you can retrieve the relevant table correctly. So it's like a 78% of the time you can retrieve the table correctly, and 56% of the time you can retrieve the column correctly. And then the quality metrics, when you get a score 4+, it's like either success, like directly or with the minor changes, like it's like 48. So it's like half, like 50% of the time you can, the SQL can directly work out of the box, which is actually good, right? So because you see the LLM, the performance even for GPT-4o or GPT-03 is only like around 20% in the enterprise setting. But with this agent framework, it's able to be improved to 50%. So actually, this is still a good performance. It's not bad. It's not bad. So this is still a good performance. And then in terms of the latency metrics, they also measure like how many LLM calls is made, how many embedding calls is made, and how many queries. Like it needs to execute the queries, because I think when you execute the query, it could also take a while to be executed, right? So under hood. So this is like how many queries they have validated and auto-tested under hood on average. But overall, they say that they're able to run it under 60 seconds per question on average. And then, so this is using all the components, right? Ideally, this is the kind of the ceiling of the performance they can reach with all the components. And then they do some ablation studies. For example, without the popularity of the table, so they exclude the information as the context to the query writer. Then what is the performance? So maybe let's look at the performance that dropped most. For example, 60%. The table coverage, retrieving the correct table, dropped from 78 to 60% if you exclude the example queries. So basically, if you do not retrieve the relevant queries, like you just throw away all the past queries or what the query the user write from the past, the performance dropped a lot. Like also for this, it's dropped from 48% to 24%, which means what user has written in the past is also very important. Context to the query writer, so that query writer can find something more relevant for the user, right? Like what tables they are using more frequently, what are the logics they are looking for. So this can all captured by the historical SQL queries that the user has created in the past. And also table cluster is also surprising to me. It's like if you do not do the table clustering, if you just put 100 million tables there, and then you want to run the retrieval directly on the regional tables, the performance also dropped because it's increased the complexity of retrieving the right tables at a large scale, rather than you can just focus on, oh, which table cluster should I retrieve, right? So you see the retrieving the right tables and also the performance both dropped without table clustering step. Which is also a surprise to me, that how effective, like how best you can organize the structure of the data is also important for the rack, for the agent performance as well. This part, the second section is on the agent, right? For example, if we remove some agent, for example, the researcher agent trying to auto-correct the mistakes, or the query fixers, or the rankers, say if I just directly put all the information from the retriever, I do not do additional step, like select the top K, with the rankers, then the performance also dropped, actually. For the performance, it's just dropped 2%. So it's not as huge as the table clustering, but it also has some like effects on this. And then this is like a ablation study of, say, if we combining both knowledge graph components with the agent configuration. If I remove or combine them or remove them, then what is the performance over there? So I would say, like, if you look at this table, I think the key part is the example queries, right? So we need the example queries. We need the additional information about the tables and columns, the attributes, and also the table clustering. So I think this is more on the knowledge graph side of how we can organize our enterprise data in the right format, in the right structure, so that the agent can utilize them effectively. Because if we don't have this information, the performance will be impacted a lot. Like without clustering, you will just get 9%. And you may say, oh, the LM agent doesn't work. But actually, it's not the agent doesn't work, it's your data doesn't work, right? So it's extremely important to organize your data and the context in the right format for the agent to consume. So basically kind of doing the context optimization to improve the performance. This is the survey they do. So if the user keep coming back, it's helped improve the efficiency. Even right now, we are not 100%, but I do believe the number is going to increase over time as we are releasing rapidly the LLMs, right? Improving the LLMs, and also the agentic framework is also improving. So I believe from 50% to 80%, I don't think the time will be 10 years, maybe maybe even less than 3 years, will be improved over time. So that's the first thing. The second thing is they also report like how, like when they deploy the chatbot, they count, for example, what is the weekly active users, and then how many of these users actually return the following week, or how many of these sessions actually got used. Like, for example, they think 33% of the chat sessions leads to basically this code get reused, right, by the user. They just copy paste the codes from this bot to the SQL editor, so that they can start with something, so that they do not need to do all the search of the tables and figure out how to write from scratch. So this kind of still tells that the user is think that it will help improve the productivity, even though right now it's only maybe able to help solve 50% of the tasks, which I think is already a good amount to begin with. And then the users, even if that SQL doesn't work out of box, they can still copy paste it, right? It is better than nothing, right? So this is like my understanding of this. And also, they also conduct a user satisfaction survey with the bot, and 40 of them think it's very good. And overall, it like rated at least passes, right? So yeah, so it's not perfect, but I think it's usable.
Yeah, makes sense. You need to have a human in the loop when to evaluate the results. You can't just use it as an atomic agent and to give you the result and blindly. Yeah.
Yeah.
That makes sense. Yeah. Thank you.
The main part of today, and I think the conclusion is, yeah, as you see, the performance is around 50%. It's not perfect. There's still a way to go to improve the performance for the enterprise like in a more complicated setting to answer all kinds of questions in a domain-specific context, right? So as we see, how you organize the data is crucial. So sometimes do not blame the LM doesn't work, blame like how you organize your data and how you organize your context to the LM. And also the second is the agentic architecture is essential, because if you just rely on one LLM, like the single LLM, even the performance may be just 20% right now. And using a agentic architecture actually can boost the performance from 20 to 50%. And maybe the next improvement could be still in terms of the context, in terms of the LLM capability itself, and also the agentic architecture that can hopefully boost the performance from 50% to 80%. But yeah, maybe next year or the year after next, but let's see. It should be there, I think, within 2 or 3 years. And then the last is the user-centric design, right? Drives the adoption. So in the end, the number does not tell much, as long as it's helpful, right? Even if it's a score of 3, it is still helpful for the users. So this to design this interactive and multi-agent chatbot can help with the strong user engagement and high satisfaction ratings as a helpful kind of like a co-pilot for the SQL writers.